Several years ago, when I was a PhD candidate studying audio signal processing away from family, I used Yahoo Messenger to stay in touch with family and friends. It was still a thing in those days. I called from a desktop, which meant no built in speakers, so wired headphones, and echo was not a problem. Webcams weren't as popular in those days, so it was an audio only call. You needed a PCMCIA card to have Wi Fi even on high end laptops, so I was on wired networks and stable bandwidth. Quality was good for an audio only call. My bar was also likely low. I was just happy to call home for free. Fast forward to today. We've come a long way, witnessed great advances in devices, mobility, ubiquitous communication, which we're going to talk about today in the context of RTC for Meta's family of apps. At the same time, these advances have introduced new challenges. Cellular networks introduce congestions and varying coverage. Calls on speakerphone are more common thanks to video calling. Microphones and speakers are closer together. Loud volume on thin form factors introduce nonlinearities, making echo a much more difficult problem to solve today. After 2+ decades of familiarity with VoIP, our users, and rightly so, have a much higher expectation of quality. New immersive scenarios are emerging in the metaverse with even lower tolerance for distortions as we seek to deliver the magic of being in the same shared space. This is an area I deeply care about. I worked on audio throughout my professional career, on Teams and Skype at Microsoft earlier, and now at Meta on our family of apps. My family, friends, and I use VoIP to stay connected, so this is close to home. Now with some context behind us, for the rest of today, I'm going to go through our approach at Meta to handling the most difficult audio challenges and a little deep dive on audio reliability, making sure audio actually works. I'll close out with looking into what's coming ahead in one of the most exciting spaces in RTC, which is fully immersive large group calls in the metaverse. But before we get to large immersive calls, let's make sure we're getting the basic essentials correct, because nobody likes this when this happens.
Okay, so
Oh, hey Phil. We can't hear you.
Yeah, I'm having the same issue. I'm not.
Hey guys, how's it going today? Everybody doing it? Sorry. Can you guys hear that? It's repeating it.
I'm really excited to share with you the updates on the project. Sorry, I think the gardener's in here. Sorry.
so that brings me to my other like our next strategy for Friday should be hopefully
So I don't know about anybody else, but
Are you
I've
talking
been
about
having
the
a lot of
spam?
issues with spam email coming into my
You
inbox,
go ahead, Phil.
and I
Go ahead.
just, I,
Christopher, you're talking about your spam box, your inbox?
To deliver reliable, high quality, low latency immersive audio, the journey starts with making sure the foundational elements are in good working order. You don't want to start every call by asking, "Can you hear me?" Excessive latency in a call reduces interactivity, resulting in participants frequently talking over one another, which is not a natural conversation. Many calls take place over low bandwidth connections, and even the best Wi Fi networks experience congestion. So, robust packet loss and jitter compensation algorithms are another important foundational element. And of course, nobody likes to hear background noise or their own voice echoed, which necessitates full duplex, high quality acoustic echo cancellation and non stationary noise suppression. Once these essentials are taken care of, the journey progresses towards enabling a high quality experience, delivering music quality, full band stereo audio, taking us one step closer to actually being there. The next step in this journey is enabling immersive metaverse audio experiences, such as spatial audio, which is key for creating the magic of being in the same space. We'll get to this at the end, but first let's talk about the essentials. Audio in RTC is not new. It's been studied for several decades. So why is this still a challenge? Billions of people use WhatsApp, Messenger, Instagram, and other apps across a variety of devices and acoustic conditions. The characteristics of microphones and loudspeakers, the coupling between them, room reverberation, background noise, distance between the mouth and the microphone, they all differ widely. And it's very unlike building audio pipeline on a single known device. We have to cater to a huge diversity of devices. To provide a good experience at our scale, our solutions and their quality need to scale from low CPU, low bandwidth connections and devices on one end of the spectrum to the most modern phones on 5G at the other end. We need to do this so we can provide a good experience to our users based on their particular device and network, all packaged in a single app. And importantly, users have a very low tolerance for audio distortions compared to distortions in other modalities. Even minor cutouts due to network distortions or disturbances due to echo and noise can be very annoying, if not even disruptive. Meta's RTC audio pipeline has its roots in WebRTC, which back in the day was a great way to bootstrap our solution. Today, most audio components have been replaced by in-house equivalents to address our new use cases, both for the family of apps and the metaverse. Talks on audio RTC typically focus on echo and noise suppression. These have seen great advances in the last couple of years thanks to deep neural nets. We even had a talk on this at last year's RTC at Scale. I'll not go into much detail because we've covered this a lot previously, but I will touch upon a few key aspects based on our experience working in this area. While modern mobile devices feature built-in acoustic echo cancelers, AECs, or noise suppressors, NS, they're built into the hardware, most apps still include software equivalents, either to cater to devices that don't have hardware AEC and NS enabled, or to provide a consistent experience across all devices where the app is operating. For AEC, there's a trade-off between echo leaks and maintaining interruptibility or double talk. A trivial solution would be to simply soft mute the microphone whenever you detect activity on the loudspeaker signal. There would be no echo leaks for sure, but there's not going to be any way for you to interrupt the remote end, and it's not resulting in a natural communication experience. Recent approaches include a linear filter-based adaptive echo canceller, the traditional kind, followed by a machine learning-based residual echo suppressor, which gives better double talk. This is often a good compromise and a good hybrid approach. Our experience at Meta, where most of the users are on mobile devices, has shown us that we do need to have a low compute baseline version that works well across all devices, the essentials, with more advanced ML models for more capable devices to get better experience. For ML-based noise suppression, an important consideration is that it's simply not trivial to decide what is and what isn't noise. That's for our users to decide. For instance, a baby crying in the background or dogs barking, they may actually be desired sounds in certain contexts. One way to address this is to have a baseline always-on stationary noise suppression to handle your typical disturbances like fan noise or air conditioners, and then offer more advanced noise suppressors, machine learning-based approaches, as an opt-in feature for users to select themselves when they feel the need for such advanced noise suppression. In this talk, we'll focus on a less spoken about, but a very critical component, audio device management, both capture and render. This addresses the audio reliability and the no audio problem. Before that, for completeness, let's quickly walk through the other components in the pipeline. Automatic gain control, or AGC, is essential to maintain normalized volume levels regardless of whether you're calling from a mobile device or a laptop or a browser, regardless of whether you're calling from a Bluetooth peripheral, earpiece, or speakerphone. For large group calls, AGC is also important to select the active participants either in an SFU, a selective forwarding unit model, or an MCU model. You don't want the loud participants dominating a conference. We'll hear more about this from Ben in his talk on scaling large group calls. Optional voice effects may also be applied at this stage in the pipeline. Next in the pipeline is the audio encoder. Low bitrate, high quality encoding is another area that's received much attention in recent years. Despite advances in network technology, markets with the largest growth in our monthly active users typically tend to happen where bandwidth is a problem, making this an important problem across industry. While it may be tempting to employ deep neural networks here, we need to remember that the devices and the users who tend to experience these bandwidth problems the most are also on devices that are typically having the most constraints on compute, low CPU devices, requiring different solutions instead of heavy ML models. The encoded bit stream is then packetized, augmented with redundancy for packet loss resilience, encrypted, and then sent over the wire as RTP packets. On the receiver, components such as the jitter buffer, the packet loss concealer, and the decoder all working together to compensate for jitter or variation in packet arrival times, packet loss, so that we can have low delay, smooth audio playout. Some implementations include gain control also in the render path to not take a dependency on send-side AGC being always available. Audio effects such as spatialization may also be applied here before the signal is then handed off to the render device manager for playout. Let's zoom in now into audio device management. This component is responsible for delivering audio samples from the microphone into the capture pipeline and from the render pipeline into the loudspeaker. This component is platform dependent and it abstracts away operating system specifics for audio capture and render so that the higher level components can now be built in a largely platform agnostic way. Components such as echo and noise control, codecs, jitter buffer, these can be developed and tested at scale in a lab using a representative database of publicly available audio files and network traces. Audio device management, on the other hand, requires physical device testing, which is notoriously difficult. Historically, audio device testing was done using a small set of devices in a lab setting. However, this quickly falls short at Meta's global scale. What may be considered a corner case easily affects millions of users at our scale. And the long tail of distinct devices among our user base meant we needed to innovate using telemetry to identify and root cause problems so we could fix them and then test them in production. Our commitment to end-to-end encryption and privacy meant this had to be done without any audio data or any user identifiable information. We built a fully privacy-compliant framework to achieve this goal. At the end of a call, randomly selected users are asked to rate the call. And for calls that are rated poorly, there's a follow-up survey where users can specify what exactly the problem was that caused them to rate this call poor. For calls where the users indicated that they could not hear audio or could not be heard, our automated framework analyzes telemetry to identify potential reasons along the processing chain. Here's an example of this framework in action. Audio problems can be introduced at multiple places in the pipeline we saw earlier. The first point of failure is if the capture device management module fails to deliver audio samples. Given the wide variety of chipsets and peripherals across a user base, this is a common point of failure. Although subsequent software components such as the echo and noise control, codecs, etc. may also introduce failures, they are less frequent and they are not device dependent. The next big source of failure is related to sending data over the network. Audio packets may be dropped due to packet loss or may never reach the other end because of transport-related failures. On the receiving end, similar to the capture side, the render device is another source of no audio problems. Let's assume, hypothetically, that users report no audio for about 1% of all calls. We are now able to break down this 1% into the categories that we just spoke about by identifying and logging error codes at different processing stages: capture, playback, network, transport, UX, and so on. Each category is then broken down into further subcategories that can be root caused and fixed. Ensuring that each of these categories is non-overlapping further simplifies the process. For instance, capture problems may be because of low level on my end or on the remote end. I may be muted, my peer may be muted. There may be device initialization errors on either end due to incorrect configurations or device peculiarities. The audio device may stall mid-call or stop providing samples to the pipeline and so on. We'll always have a non-zero percentage of problems categorized as unknown. In our experience, users, rightly so, sometimes tend to interpret the survey choices differently. For instance, selecting no audio when there was only a momentary loss of audio because of a transient network artifact. These are still important problems and we handle these as part of our network resilience efforts, but we may not want to include them as part of our no audio problem. Based on the error codes we logged, we were able to root cause and fix several issues. Some examples. We saw a good talk time improvement by alerting users through a pop-up notification when they were talking while muted. Here's another example. I had to take a work call from my phone one day as my laptop was installing mandatory updates. I'm sure we've all gone through this at some point. What was different this time was that I lost audio all of a sudden. Turns out that my wife had pulled into our driveway and my phone paired with her car's Bluetooth. This was embarrassing and a lesson learned to only pair my phone with my car, but Bluetooth devices are a common source of failures. Unexpected pairing, like in this example, dead battery, etc. Having a good UX and related notifications are also critical for audio route management. Another example is a no audio bug we fixed on Instagram on iOS. When another app that also accesses the microphone is active, for instance, a video recorder, making a call on our Instagram app would result occasionally in no audio. This behavior on iOS makes sense when you receive a phone call while listening to music. iOS interrupts the execution of the foreground process, and the application, or the audio session linked with this application, gets deactivated until the interruption has ended. However, in our scenario, when the user explicitly displays intent by placing a call or answering a call, we found the Instagram app to still be deactivated in its audio session. Once we found this root cause from our logging, the fix was simple. Simply disregard the interrupt when we are in an active session. This and many other fixes end up being very simple in hindsight, like they always are, but the key is having a good framework to uncover root cause and fix these issues. Not everything is smooth sailing. We've also had to tweak things along the way. Since audio stalls were a major contributor in our breakdown, we implemented stall detection and recovery. If the audio device fails to provide callbacks for longer than a certain duration, let's assume 2 seconds in this example, we enter this recovery mode. But it turns out that when you're trying to switch your audio route from the speakerphone to a Bluetooth, it takes longer than 2 seconds and it incorrectly triggers the stall recovery. So we've had to go back and revisit our timers and tweak some of these thresholds. The key here again is having a methodical approach to identify root cause and then continuously improve along the way, which this breakdown and framework provides us. In traditional video conferencing, each participant is in a different room, and as we see everyone located in these different environments, to some extent our mental model accommodates resulting differences in audio quality. In a metaverse setting, however, where we aim to deliver the magic of being in the same shared virtual space, the tolerance for various audio distortions is very low, since we don't experience any of these when we are all physically present together. As the participants are joining the call from their own rooms, each with their own unique acoustical characteristics that need to be compensated for, all of the problems we discussed so far, echo, noise, latency, etc., assume a new level of importance. When talking about large calls with hundreds of participants, there are also problems of client and server scaling. Traditional methods of audio capping will not work in such a context where you want to hear not only the people in your conversation, not only the people in the conversation you're part of, but also conversations happening on the side, just like you would in real life. Sending dozens of mono streams from all the participants to each client where they can then be spatialized will provide a realistic experience, but it will strain the client's network. Generating a single ambisonic mix on the server for each downstream client can address the client bandwidth problem, but spatial accuracy is going to be limited. We'll need an intelligent, hybrid, proximity-based approach that strikes a good balance between scalability and quality. These are exciting times for audio where we need to not only solve the old traditional problems with renewed vigor, but also solve new emerging use cases like these immersive metaverse calls. I look forward to engaging with this community as we solve and address all of these challenges ahead of us. Thank you.